We can start.
Hello, everyone. I will continue with this course on the astrophysical stochastic background by Professor Vuc Mandic. Vuc, please take it away.
Okay, thank you, and welcome everybody again. So I hope you can see my scratch pad here on the screen.
Yes.
Where we left off yesterday, just to remind everybody. So we wrote down the energy density in gravitational waves, which remember we defined it as 1 divided by the critical energy density, or we could write it as F divided by in the numerator, and then this would be d rho df. We wrote this down in terms of the flux. So we could rewrite this whole equation as the frequency divided by the speed of light and rho, the critical energy density. And then we have the derivative of the flux, energy flux in gravitational waves with respect to the frequency. And the flux, or df, we argued yesterday could be written as an integral over redshifts. So the integral from 0 to infinity in principle over redshift. And there are several terms that show up there. We had the rate of sources, whatever those sources may be. So things like binary black holes. We have to divide by the area of the corresponding to the distance at which the sources are sitting. So dl here is the luminosity distance. And then we had the factor of 1 over 1 plus z to account for the energy reduction in gravitons as they travel. And then finally, the EDF is which is evaluated at the frequency at the source, which is F times 1 plus z, right? So the story here, if you remember, was that if the Earth is here, we're basically looking at some sources some distance away. So this would be some redshift z, or similarly some corresponding luminosity dl. The proper coordinate in cosmology, if you're familiar with that, would be some r. So we're looking at this range here of in redshift dz, and counting up the sources that are gravitational wave sources that are sitting in that shell of size dz, such that all sources from that shell would produce energy spectrum df, which would first have to rescale by this factor of 1 plus z. Then we will have to multiply this by the rate, so how many of such sources there are per unit time. And then, of course, to calculate the flux, we have to divide by the area, which will be the area of the sphere of radius dl. So that's this 4 pi dl squared. Now, it turns out, just to make this a little bit more tractable, we can manipulate this rate a little bit more. So the r of z in here, this is basically the rate of sources measured in our local time at the Earth. And it turns out to be convenient to express this in terms of the rate per comoving volume. So in other words, we will write something like this. The rate, as we observe today, would be the rate per comoving volume, and this is basically defining the volume that expands with the universe, right? Divided by 1 plus z. And this factor of 1 plus z accounts for the time difference, right? The RV is the rate per comoving volume, so it uses the local time. It uses the time of the source itself in the source frame, whereas the R of z is our local time here on Earth, and the two are related by this factor of 1 plus z. And then we have dv dz. This is basically accounting for the fact that R of z is the rate per unit redshift, whereas this RV of z is the rate per unit comoving volume. And the comoving volume can be written in terms of the proper volume as 1 plus z cubed times dv proper, where dV proper is the volume in the usual coordinates, so you can write it as 4 pi r squared dr. That would be the volume of this shell that we are looking at. So here r is the proper coordinate, and we have r squared and dr, so three powers of r. So we have to scale this by 3 factors of 1 plus z to get the actual volume today. So that's so 2 of those powers of 1 plus z and r. So we'll use the fact that 1 plus z times r is the luminosity distance. Okay, so this is the distance you would use when you're calculating the flux, for example, as we did earlier on. So this ends up being 1 plus z times 4 pi dl squared times dr. Okay, and then finally we use one last piece of cosmology, or one last piece of information, I guess, from cosmology, which is the relationship between the proper distance r and the redshift z. And I'll just cite this, or just give that relationship. We're not going to go into the, dealing with this would be a course in itself. So we'll just use the result. I will write it down and then I will explain what all of that is. So c, of course, is the speed of light. H0 is the present value of the Hubble parameter, so about 70 kilometers per second per megaparsec. And this part here is the evolution of the Hubble parameter, right? So this is the energy density in matter. It's a number of about 0.3. And the 1 plus z cubed captures the evolution of the matter during the universe, or the matter energy density, I should say. And the last term here is the dark energy density. So it's a number of about 0.7, and it's independent of redshift. So it's not multiplied by the factors of 1 plus z. So now we have all of these pieces that we can put together. If we want to calculate r of z now, we can, instead of, well, we'll first have r v of z divided by 1 plus z, okay? And then we want to write dv dz, which has several factors. So first we have this factor of 1 plus z times 4 pi dl squared. And then we have dr dz, so that's basically this contribution here. So we have another factor of c divided by h0. And then we have 1 over the square root of omega matter, it's 1 plus z cubed plus omega lambda. Okay, and then we take this expression and plug it into our expression for the flux, and then for the omega GW. So putting all of that together, we have omega GW, which is a function of frequency. We have the this prefactor here, okay, f divided by c rho c. So f divided by c and rho c0. And then we have the integral over the redshift. And then let's see, I forgot one piece. I know, we're good. So we have, instead of r of z, we will have the expression I just wrote. So I guess I'll write it all again. RV of z divided by 1 plus z. Sorry, the 1 plus z's here will cancel, so we can at least get rid of that part. Okay, so we have another h0 here. We have 4 pi dl squared c. We have a square root of omega matter, 1 plus z cubed plus omega lambda. Okay, so that's the part coming from r of z. And then we have the rest, which is this part here. So we have another factor of 1 over 4 pi dl squared. We have a factor of 1 over 1 plus z, and we have the E df evaluated at 1 plus z times f. Okay, so now a few things cancel. The 4 pi dl squares cancel. The c's also cancel. And what we're left with is f divided by h naught times rho c0, okay, times the integral over the redshift. And we have r v of z divided by 1 plus z times the square root, write it out again, omega matter times 1 plus z cubed plus omega lambda. And I believe the only other piece left is the EDF, which is evaluated at f times 1 plus z. So this is our final expression. So I'll box it up because that is the final formula we will use to calculate the energy density in the stochastic background due to different astrophysical models. And when you look at this, you see that a lot of this is well known, right? So f, of course, is just frequency. H naught is a number. Rho c is a number. In the denominator here, 1 plus z, of course, we're integrating over, so that's not a problem. The expression here under the square root is also well known. We now know the values of omega matter and omega lambda pretty well, 0.3 and 0.7 respectively. So really what's left is, and maybe I'll just box this up with a different color, is these two last terms. We need to know the rate of whatever sources we're dealing with per co-moving volume. So this will be the number of, let's say, black hole binaries per megaparsec cube per year or something like that. And we need to know DEDF, which is the actual energy per unit frequency emitted by each of our sources. So now at this point, we basically we have reduced the problem to we have to pick a model, and then we have to for that particular model we have to define or decide what the rate of those astrophysical objects is. So that's our RV. And we need to calculate usually from first principles or make some sort of an estimate of how much energy is being emitted per frequency for that particular model. So maybe I can stop here for a second in case there are any questions. Our next step will be to actually apply this to specific models and see what happens. Let me see if I can open up the chat as well. For some reason I can't see the chat.
And no questions on the chat so far.
Okay. All right. Very good. Okay. Well, let's then press on. So what we will do the next step is we're going to do to apply this to the compact binary coalescences. Okay. So again, as I said, we're going to use this master formula, but we will adjust the RV and DEDF for each model. So for the compact binaries, as you probably know, these are compact objects. So we're dealing with either black holes or neutron stars, which basically have mass that's of the order of solar mass. So it could be a few times the solar mass, or it could be even tens or 100 times heavier. But it's compactified, right? It's the star has collapsed into either a neutron star or a black hole. So its physical size, in the case of a neutron star, would be about 10 kilometers. In the case of a black hole, of course, we're talking about a singularity. So we have this large mass that is compactified in a small amount of space, which means that two such objects can get rather close to each other. So if we have two black holes, they could rotate the gravitational bound with each other. They could rotate around each other, emit gravitational waves. And as they emit gravitational waves, they get closer and closer, and they eventually merge. Now, if we were dealing with objects like regular stars or even white dwarfs, the physical size of these objects would be thousands or millions of kilometers, which means that these two such objects would collide, would touch each other at much lower frequencies as they inspiral towards each other. Their smallest orbit would be defined by their physical size. So that would be of order thousands or millions of kilometers, which means that they would be merging at the frequencies on the scale of millihertz or even lower. But for black holes and neutron stars, their merging happens, or their last orbit happens to be much smaller, so of order tens of kilometers or even less. So in that case, that last orbit corresponds to very high frequencies. They're moving around each other very fast. So those frequencies end up being tens or hundreds of hertz, which is in the frequency band of the terrestrial gravitational wave detectors like LIGO and Virgo and so on. So that's why the binary, compact binaries that involve black holes and neutron stars are of particular interest to LIGO and Virgo. So we're dealing with such systems. These are two massive objects that inspiral around each other, and eventually they merge. And from general relativity, we can calculate what the EDF is for such systems. And it turns out, I'll just give the expression here. So we have pi to the power 2/3, g to the power 2/3. We have the chirp mass, I will define that in a minute, to the power 5/3, all divided by 3, times the frequency to the power -1/3. And the chirp mass itself is a very particular combination of the masses of the two objects in the binary. So if we define two objects to have masses m1 and m2, and they're revolving around each other, then the chirp mass would be defined by m1, m2 to the power 3/5 divided by the total mass m1 plus m2 to the power 1/5. So this quantity, as you can see, still has the units of mass, but it's a very particular combination of these masses that becomes important. And the other thing that you notice is that this DEDF goes as the frequency to the power -1/3, and that immediately tells you, if you go back to our master equation, so there will be f to the power -1/3 coming from here. There is no frequency dependence here. This is the frequency of the gravitational wave source. So the rest of this master equation here has nothing to do with the actual source. So we have f to the power -1/3 and f to the power 1 out front, which means that the energy density for compact binary coalescences will go as f to the power 2/3. Now this piece, this is really the most important aspect of the gravitational wave spectrum for the CBC model. What I've described here is this part DEDF is really applies to the inspiral part of the evolution of the binary. So on the part where they're revolving around each other. It does not really account for the merger and the possible ring down after the merger of the two compact objects. Now you might worry about that because the merger tends to actually be the loudest part of the waveform. That's where most of the gravitational wave energy is emitted. However, it turns out that the merger for most of these compact binaries that we're looking at here happens at relatively high frequencies, hundreds of hertz or even in the kilohertz range. And that's quite a bit outside of our sensitivity region. And this is not just because the gravitational wave detectors have strain curves that look like, so if I plot strain as a function of frequency, I'm sure you have all seen the sensitivity of LIGO and Virgo and so on looks something like this, where this turnover happens at about, let's say, 200 hertz, roughly speaking. So the sensitive region tends to be, maybe between 20 or 10 hertz and 150 hertz. But it's even worse than that because remember that what we discussed last time, there is an F cubed relationship between omega and H. Omega, the gravitational waves, behave like F cubed times H of F, where H of F is the strain power. So this factor of F cubed really pushes us to even lower frequencies. So most of the sensitivity in the stochastic searches will actually come from 10 to or 20 to 50 or 60 hertz. And by then, in that region, we basically have no contribution from the merger and ring down. So while merger and ring down are in principle important and contributors to the energy density overall, we don't really have a chance of seeing them with LIGO and Virgo because they tend to happen quite a bit outside of our region in frequencies where we are sensitive. The only way merger and ring down can contribute to 50 hertz is if they happen at a very high redshift, so very far away. If a merger happens at a redshift of 7 and at the frequencies of, let's say, of 700 hertz, then we will observe it at about 100 hertz. But redshift of 7 is rather far away. There aren't many sources at those distances anyway. So again, we don't get much from the merger and ring down. So I hope this makes sense. The point I'm trying to get across is that when we're dealing with the compact binaries, for the stochastic part of this, it's really the in-spiral part of the evolution that matters. The merger and ring down is typically at higher frequencies, and even if we account for redshift, it does not really contribute significantly to the energy density in the stochastic background. So that's one piece. So we have the DF. Remember that we I should say one more thing. So when we write the DF in this particular way, as you see, there is chirp mass showing up here, which depends on the masses M1 and M2 of the binary. So written this way, this is this DF describes only systems with that particular chirp mass. But we know, of course, that binaries come with a variety of masses, M1 and M2. So you can try to make your model a little bit more complex. You can try to account for the variations in the chirp mass or the individual masses. So for example, one way you can make your model a little bit more complex is to write DF. So we have the same prefactor of, let's say, pi g to the power 2/3, f to the power minus 1/3 divided by 3. And then instead of just using the chirp mass to the power 5/3, we can try to use an average chirp mass over a population of binaries. So one way to do this is to integrate over some probability distribution of chirp masses. And then, of course, we need m to the power 5/3 here. So what we're trying to do here is rather than using a single value for the chirp mass, we can try to average over a distribution of chirp masses where that distribution is given by this P of M. And this P of M is now maybe known because we have seen quite a large number already of, let's say, binary black holes. So we have some idea of what the chirp mass distribution should be, and we can use it in this calculation. You could also, if you don't want to deal with the chirp mass, but with the individual masses, you could also write the df in the same way. The prefactor would be the same, but then we could have the double integral over masses m1 and m2, and then we have some probability distribution of m1 and m2 rather than the chirp mass, and then chirp mass to the power 5/3. So that's another possibility. And in fact, this last thing is what we're using in our papers recently. We basically use the distribution of masses that is coming from the studies of the individual binaries from LIGO and Virgo detectors, and then trying to and then do this kind of an integral over that distribution to account for all the possible values of the chirp mass. Okay, so I hope that's okay. This is what we have in terms of DEF for this model. Remember that, so that's only one part. We also need to specify the rate of these sources. So we need to talk about the rate per co-moving volume.
Vuc, is it a good time to talk break for a couple of questions?
Yes, absolutely. Please go ahead.
Okay, well, I have a question myself. One is about this argument about why the merger and ring now does not matter. So you told that the omega goes as f cubed times the h of f. So I would have thought that this would basically amplify the high frequency part. So why do we? What is a? How can I see that the high frequency part not contributing?
Just a second. Maybe I've gotten this wrong. It wouldn't be the first time. Let's see. So the omega is f cubed h of f. I think that's right. So the way to think about this is if your detector has certain sensitivity at 100 hertz, it will have some sensitivity to omega. If it's if you somehow make the detector equally sensitive at 10 hertz, then you will be sensitive to a factor of 10 cubed, a smaller value of omega.
I see. Okay. Yes.
Right. So it does look a little bit strange, but think about this H here as the level of sensitivity of your detector. That tells you the level of sensitivity in omega.
Right. Okay. Right. There is the other question from Vikas, which is if the stochastic wave background is due to contributions from stellar mass black hole mergers or BNS mergers, which are transient, would we still expect the stochastic background to be permanent?
That is a very good question. The answer is that we're really more in the popcorn regime here. We're integrating over the entire population in the universe, and based on the local rates of observed individual black hole and neutron star binaries, we expect that there will be, I think, a black hole binary merger every 15 minutes and binary neutron star merger every minute or so, if I remember the numbers well. This is not a continuous, and it's not a perfectly stationary background in that sense. So there are fluctuations due to the fact that the number of mergers in any given time segment will vary. I guess two comments about that. The technique that we use to search for the stochastic background really measures the energy density in the data we acquire. It doesn't matter really whether the data whether the background is perfectly stationary or it's popcorn-like. Even if you had a single event, you could search for that event with the stochastic background technique, but it would be a very inefficient way of doing it, because you would be combining that one event with a lot of just noise. So it wouldn't be a very, very good way to do it. having said that, there are ways in which you can improve the sensitivity to searches for this type of a background to exactly account for the fact that the background is not there all the time, so that there is some duty cycle, and to account for the fact that you actually know what the signal looks like. So I will, well, we can see maybe on Friday, if we have time, I may say a little bit about it. That goes under the name of the Bayesian search, and it has not yet been actually implemented. There are efforts by multiple people in the LIGO and Virgo collaboration to devise that kind of a analysis pipeline to search for the popcorn nature of this kind of a model. What we will discuss more today and tomorrow and on Thursday, I guess, is focused on cross-correlation search for the stochastic background, which makes no assumption about what the model is like. So it can certainly be used to search for this model, but it might not be the most effective way to search for this particular model. Does that answer the question?
I think so. Thanks.
Yeah. Okay. All right. So let's see. Where were we? So we wrote down the F. We need to write down something for the RV, and there to find the rate of how many binary black holes per co-moving volume per unit time there are. And remember, we need to know this as a function of redshift. So if we assume that that our compact objects are of stellar origin, so they're stars that collapse, then we can assume that the RV of Z is related to the star formation rate. Okay, so this is the rate at which the stars are formed. And this quantity is actually relatively well known. It's something that is measured by the astronomers. Let's see, I can probably show. Let's see, where are we? You should be able to see my screen here. Maybe I'll.
Yes.
A little bit bigger. Okay, that may be too big. This is the there are many papers out there studying the star formation rate, and this is one that I was involved in, so I know it may be the best, but the results tend to be consistent with others. The different contributions, different authors are agreeing more and more on what the star formation looks like. So as you can see, there is a lot of data at low values of redshift. The x-axis here is the redshift, the y-axis is the star formation rate. And you see that there is a lot of measurements at redshifts down below, let's say, 5. And you see that the star formation rate, as you go back in time, it increases. It peaks at around the redshift of, I don't know, 1 or 2. And then decays away as we go further back in the history of the universe. Here we're entering the times where the first stars and galaxies are being formed, right? So this part of the curve is not well understood. You see, there are only a few data points. They have large error bars and so on, but this part is very well understood. So for us, this part doesn't contribute very much because these are objects that are very far away, and there are very few of them. They will be contributing relatively little in terms of their energy density here and today. This part is what matters the most, and typically what we do is we fit some sort of a curve to these data points just so to make things more tractable and calculable. So what we usually, one of the functional forms that we use for the star formation rate looks something like this. There is some normalization factor, and then there is a piece where we have an exponential increase. So that would be it will look something like that, and then there would be an exponential decrease, which would have a different exponent, so z minus zm. So zm here basically defines the peak, and A and B define the rising and the rising and decaying time constants, or z constants, I guess, since this is in units of redshift. So A and B and Zm, they're all of order 2 or 3. Okay, and I've given the exact numbers that we use in some of our papers. You can find them in the notes. There are variations here. You don't have to use this particular form. There are others as well. But as I said, for redshifts below, let's say 3, things are reasonably well behaved, and different authors agree. And so you may get a factor of, I think at this point it's less than a factor of 2 variation due to different star formation rate assumptions. And this new here is basically the normalization, and its value is 0.146 times, it's in units of the solar mass per year per megaparsec cubed. So anyway, that's the star formation rate. And again, this is the rate at which the stars are forming. That's not exactly what we want, because what we want is the rate at which binaries are merging. So we need to somehow take into account the fact that there is a time delay, basically, between the formation of stars and the time when a binary would merge. Okay, so this is the time during which the star lives its own life cycle, collapses, but also gets connected with another star or black hole and so on. And then that binary now has to do its thing, the in-spiral dancing, until they merge. So this can take a long time, and it is the process itself is not very well understood yet. There are population synthesis models which look at how this kind of time delay would look like, and what are the constraints, the minimum maximum delay times, and so on. What we do in most of our studies is we basically try to account for our ignorance by marginalizing over the time delay. So in particular, we write something like this. So this is our rate per co-moving volume of mergers. We write it in this way. So we have a factor of lambda. Give me just a second to write it down, and then we can stare at it. Okay, so TD here is the time delay. And what we do is we're looking at the rate of mergers at some particular redshift z. We calculate the time corresponding to that redshift, subtract the delay time, okay, so how long that particular object had to basically go through its life. That gives me the time at which the object was formed. And that should be what I need is the rate of formation at that particular time. So this here is the time at formation, which is the time at merger, T of z, minus the delay time. So that gives me the formation time of the binary. I calculate the star formation rate at that time. And then since I don't know what this TD is, I try to marginalize over it, to average over it, basically, assuming some probability distribution for the time delay. And this integral goes from some minimum to some maximum time. Okay. What we do in our papers is we assume that P of t, or TD, goes as 1 over delay time. This is a little more than a guess. It is consistent with some population synthesis studies and so on. But is the power exactly -1 or -1.5 or -0.7? That's not really, at least as far as I know, it's not well understood. It also doesn't matter too much because this integral is really dominated by the minimum time for the time delay. So slight variations in the exponent in this functional form don't matter too much. What matters is what you choose for the T min to be. And for the binary black holes, we assume the T min to be T min to be 50 megayear. Okay, so this is basically saying that if we have a binary black hole, it will take at least 50 million years for it to merge. And for the binary neutron star, we assume it to be 20, I believe. Let me just double check. Yeah, 20 megayear. These are also basically guesses. But again, they're consistent with population synthesis studies. Let me also show you, so we can go back to the next slide here. Oops. Yeah, that's what I wanted to do. So at some point in the past, we did a study of how much different choices of the time delay distribution, how much they matter. So we looked at several values of the power index. So here's the P of t is assumed to be time to some power alpha, where alpha, we looked at values of -0.5, -1, -1.5. We looked at a few different values for T min. For T max, it doesn't really matter. That doesn't contribute very much to the integral. But we typically assume it to be basically the age of the universe, so 13 gigayears. And what you see here are, depending on what we choose for the model, which values of alpha or T min we choose, and here are different choices. This is for advanced LIGO on the left, and for the binary neutron stars on the left and binary black holes on the right. What you see is that changing the population, the time delay distribution model doesn't make a huge difference. It's of the order of factor of 2 in terms of what we can decide or what we can say about various parameters of the model, like chirp mass or this factor of lambda, the rate of the binaries and so on. So this is to say that we don't really know what this time delay distribution is, but we can try to model it, and in the end, it had our ignorance of this time delay distribution introduces potentially systematic errors at the level of a factor of 2 or so. So that's something to keep in mind, but and perhaps when we have enough sensitivity and so on, we could start to even constrain this time delay distribution model. Okay, so that's so we have now our V. I should add one more thing, which is that there's another wrinkle that you can think or worry about, which has to do with the fact that massive black holes are formed preferentially in environments that have relatively low metallicity. And metallicity also, excuse me, also evolves with redshift. So you can try to account for this double redshift dependence, if you like. And as an example, if you look at the LIGO Virgo stochastic background search for the O2 run, so for the second observation run with advanced LIGO and Virgo detectors, the assumption we made was that if you have a binary system that has at least one black hole that's more massive than 30 solar masses, so if we have a binary system that has one very massive binary, then for such objects, the star formation rate would be reweighed. And the reweighing would be done by this fraction of stars with metallicity smaller than 1/2 of the solar metallicity. So we would take into account the evolution of the metallicity with redshift when dealing with such massive systems. Again, this is something that it comes from the astrophysics and population synthesis and so on. There are arguments, pro and con, how one should deal with these things. Again, in the end, we're dealing with factors that are at or smaller than a factor of 2 in the final results. So the upshot of all of this is that our model, this master equation that I presented, comes with, it works reasonably well, but there are wrinkles. Once you start to actually go through the details, there are things that come up, like what is the distribution of the chirp masses, and how do you treat that? What is the distribution of time delays? How do you treat that? Do you worry about these massive black holes and the metallicity impact and so on? And when you put all of that together, your model can be more complex, and it can include things that you maybe learn from astrophysics or population studies and so on, from things other than the gravitational wave physics itself. So just to give you an example of what the results look like, these are our calculations from the LIGO and Virgo collaboration for the last stochastic search. So you can find that on arXiv. This is the 03 stochastic search paper. On the left-hand side, what you see is there are 2 bands here. The darker one here corresponds to the binary black holes, the lighter one to binary neutron stars. You see that in this low frequency region, so below 100 hertz or so, you see that both bands increase roughly or follow roughly the f to the power 2/3 law. So that's basically coming from the fact that we're really just sensitive to the in-spiral part of the binary waveform, binary merger waveform. Now you also see that they start to turn at frequencies above 100 hertz, and the binary black holes turn faster than the binary neutron stars, and that's simply because the binary black holes merge at lower frequencies than the binary neutron stars. The 2 bands have different widths, so you can see that the width of the binary black hole band here is smaller than the one for the neutron stars. And that simply has to do with our uncertainty in the rate. We have seen many, many more binary black holes than binary neutron stars at this point. So it's something like 50 to 1, I think, at this point, or roughly so. Either way, the Poisson errors on the number of binary black holes are much smaller than the Poisson errors on the binary neutron stars. And that's reflected in the width of these 2 bands. The dashed curve was calculated under the assumption that we have not observed any neutron star black hole binaries. So this was the kind of the maximum or the upper limit on what the contribution from the neutron star black hole binaries would be based on the lack of the observation of them. And then if you put these 2 together, you would get this on the right-hand side, this blue band, and that's our at this point our best guess of where the stochastic background amplitude should be as a function of frequency for the compact binary systems, combining neutron stars and black holes together. Compared with that, here is the sensitivity of our actual searches. So we will talk a little bit more about that in the coming days, but This solid black line is basically what we would refer to as our upper limit. And you see that that is about an order of magnitude or so above where we expect the actual background to be from the compact binaries. So we have not seen the background yet, and we did not expect to see it. We're still about an order of magnitude away. But you see the sensitivities of these future future runs. So this one here, the dashed curve, is corresponding to the design sensitivity. So that would be our 04, the fourth observation run, which is scheduled to start next summer. So you see we're hoping to get pretty close with that. And then a couple of years after that, we'll have the A+. So that's the upgraded advanced detectors. And with that, we actually hope to at least see a glimpse of the stochastic background. And that's the time scale for that is of order of 4 or 5 years, I think. So we think this is coming. We think that this background will be detected in the coming few years. And again, these curves correspond to the cross-correlation search technique that we will talk about tomorrow and the day after. It is not this optimal Bayesian technique that I mentioned earlier for the popcorn type noise, which may actually be quite a bit more sensitive if we get it to work. And it may result in a detection sooner as well.
Can I ask a question?
Absolutely, yes.
So from the plot on the right-hand side, where you have plotted the noise and the noise properties of the detectors and also the spectrum, the omega GW, is there a intuitive way to understand what the SNR of the signal would be just from this plot?
So the calculation might be a little bit more involved, and I didn't want to go through it here, but the interpretation is that if this curve intercepts a model predicted curve, then we would observe that model at the level of sensitivity of that curve. So these are given at 2 sigma. These are power law integrated curves at 2 sigma level. So if, for example, this curve here intercepts a model, we would see that model at the level of 2 sigma. So if it's just touching it, right? In this case, you see that we are actually digging deeper. So if I were to compare the A+ sensitivity with the mean sensitivity, or the mean prediction of the model, then I would think that we're probably at the level of something like 3 sigma for that particular model. If the model happens to be at the lower edge of this band, then we would be maybe at a 2 sigma sensitivity. Does that answer your question?
So does 3 sigma essentially also mean SNR equal to 3?
Yes, exactly.
Okay, right. Okay, fine, thanks. And okay, so what is the typical value of the SNR needed to claim a detection of the stochastic background? Is it something like 5?
Yeah, so that's an excellent question as well. People differ on this. They have different opinions and so on. I think we have basically adopted in the stochastic group of the collaboration SNR of 5 as the level where we would claim detection. But SNR of 5 will not be obtained overnight. So it's not like we'll turn on a new version of the detector and we'll come up with the SNR of 5. My own expectation is that maybe we will see SNR of 2 or 3 with 04 or 05, and then we will wait for the next better detector or run longer maybe to increase our sensitivity, and that will slowly bump us towards SNR of 5. It is also possible for these other Bayesian techniques that are more sensitive to get there faster. So then we may have 2 different approaches, one that is model independent and one that is model dependent, and they will have different sensitivities. But if they support each other, if they're consistent with each other, then we may be able to claim a detection sooner. But in my mind, this will be a gradual process that will probably take a few years before we get to the point of we'll probably initially have hints of the signal, and gradually improve our sensitivity and our significance to 5 sigma level.
Okay, thank you. That makes sense. Thank you.
Can you take a few more questions from the chat?
Yeah, absolutely. I can't see the chat for some reason.
Yeah, that's fine. I'll read it for you. I'll start from the most recent one. So one is, do we see these signals at a lower SNR in the past runs?
No. So all of the past runs, including this one here, have resulted only in upper limits. So no detection yet.
Mm-hmm. So then I'll go back from the previous content. Kaushik is asking, what can we say for a more complicated probability distribution for the time delay? Other than a power law time delay model.
Yeah, so that's another good question. I'm not an expert really on this question, but from what I understand from the population synthesis models and so on, the models tend to predict something like this, something like a distribution that slowly decays with time. So you can try more complex time delay distributions, but if you want to be consistent with population synthesis, you don't have a huge amount of room to play. So of course, if you make if you say that the minimum time delay is 1 billion years, then there will be no mergers and you will see no background, right? So you can of course, if you push your time delay model to extremes, you can make a very large differences in the prediction of the omega GW. But if you want to be consistent with population synthesis models, then that will force you to keep your time delay distribution relatively close to 1/t. And in that case, the variations in omega are at the level of factors of 2, not much more than that.
Mm-hmm. Okay, I think the next question is related to a master equation for the omega GW. The question is this calculation valid for different systems like MREs, EMREs, equal mass, supermassive black holes, etc.?
Yes, I think the master equation should be just fine for all of those cases. I'm trying to think if there is anything I missed.
Did we lose you?
Oh, it looks like I may have been muted. Oh, now I see the chat window. Something just happened. Can you hear me okay?
Yeah.
Okay, sorry about that. Yeah, I was saying that I think the master equation should still hold, but there may be differences in. So certainly the rate per unit per co-moving volume will change. You have to account for that because you're dealing with, let's say, much more massive objects and so on. But and also the DEDF may be different because if you're dealing with highly eccentric systems, that may change the rate at which the energy is being emitted as well, but from a single source. So I would say, yeah, the master equation would probably be fine, but you would have to tweak the DEDF and the RV to account for the model differences.
Mm-hmm. There's also a related question about this, the way you argued about neglecting the merger ring down. So Sajad is asking, for future detectors which has a much larger bandwidth, would this approximation be still valid?
Yeah, unfortunately, I think it would be. I think so. Let's see. You can see that yeah, the bandwidth is increasing, but so I don't have the Cosmic Explorer and Einstein telescope here on this plot, but they would be about an order of magnitude below these curves. So something like 10 to minus 11, 10 to minus 12 even. But the bottom will be at about the same place. And the reason for that is that this F cube factor is just so powerful. So it really, even though these future third generation detectors will have better sensitivity, they will still not be able to probe this part of the spectrum. Not very much, at least. So, but I think this is something that we should keep an eye on. You know, things look like that right now. Maybe our understanding of the models will be different. Maybe we'll learn more about them and so on. And it would be really great if we could probe this part of the spectrum, you know, 100 to 200 hertz, because, or 300 hertz, because they're, you know, then you can start using that to distinguish different contributions, the binary black holes from binary neutron stars, for example, and so on. Because as is, with our search, we'll measure everything lumped together. We will not know whether it's coming from neutron stars or black hole binaries or black hole neutron star binaries and so on.
Okay. So Shashwat has a very interesting question. Would the stochastic background become a source of background noise for future detectors, say 3G,
Yes.
trying to detect transient signals, and would therefore contribute to the noise PST?
I think I looked at that a few years ago, and I think it will be, we will need to worry about it. It really depends exactly where that background ends up being, whether we're at the very top of our predictions or at the bottom of our predictions. But depending on that, it may or may not actually limit the sensitivity of the third generation detectors.
Thank you. I think we are done.
Okay. Okay. So let's see. What I wanted to do next is, so this is basically the discussion I wanted to have about the compact binary objects. We can have we can go through the similar kind of calculation for other astrophysical objects that produce gravitational waves as well. So one example is the stellar core collapse. So maybe I should switch back to my slides here. So the stellar core collapse, what we mean by that is, as you know, the star lives its life burning hydrogen, creating helium, and then from helium creating oxygen, and so on. The process eventually stops when the star runs out of the nuclear fuel, and at that point the gravity starts to overcome this pressure from the fusion reaction and so on. And in the case of neutron stars, the collapse basically means that all of the nuclear material will be squished into effectively a giant nucleus of about 10-kilometer radius. In the case of black holes, the collapse proceeds even further. So that's for even more massive objects where the gravity is even stronger, and we end up with a black hole. The process of the core collapse is a very messy one, and there are many processes that take place more or less systematically. So there are for example, there are magnetic fields that may be present. There are shock waves going through the matter. The neutrino flow is very important because that is basically how these objects cool. So that the transfer of heat through neutrino flows and so on is very important, and so on. So all of that is rather difficult to model, and there are people whose career is basically focused on understanding this process of the stellar core collapse. And there are sophisticated simulations, 2D, 3D, including some or even all of the known physical processes and so on, that try to basically simulate how these collapses take place. During this, so what I'm showing here is a result from one of the simulations by Christian Ott, and you can see the kind of mass non-uniformity in this stellar core collapse. You see that it's not spherical, and so again, we're in a situation where we have large masses moving relatively fast, and that, of course, results in the gravitational wave production. And there are, again, multiple contributions to gravitational waves during this process. There are shocks that move the matter around. There are hot bubbles that are expanding. There is something called the standing accretion shock instability, or SASI, which may or may not happen, and so on. So the upshot of all of that is, or the message I'm trying to get across is that the stellar core collapse process is another situation where we have large masses moving relatively fast. So we expect gravitational waves to be produced, but exactly what the waveform should be for those gravitational waves is far from clear, and it probably will depend significantly on the individual object that's collapsing. As I said, there are simulations out there that try to simulate the collapse, and during the collapse also calculate the gravitational wave emission. And I wanted to show a couple of those. These plots come from a paper that a student of mine did a few years ago, and we're actually revisiting these now as well. What you see here is this jagged line is basically the prediction of a particular simulation. We don't do those simulations. These simulations actually came from other papers, like this one here came from Avdi Kamalov et al. This one here came from Berhan Miller et al. But the reason I'm showing them here is to just indicate, at least in these two models, it looks like there is a peak at about a few hundred hertz or so in gravitational wave production. So, and these are just some examples. There are many others that look very different. It might not even have the high frequency part, and they may have a low frequency part that's maybe peaking at 600 hertz or so, maybe even lower. So what we try to do is, instead of trying to calculate the DEDF for these models explicitly, we actually try to empirically fit these simulations using some sort of an empirical functional form. Just to give you an example, what we did was we assumed that DEDF, so we're now talking about a core collapse. We would say that DEDF it looks something like this. So we have an expression that looks like this. So it has the right units out front, and then we have the neutrino energy. So this is the energy carried away by the neutrinos. There is some average Q, which is basically the average neutrino anisotropy. So this piece here is basically telling us the level of gravitational wave emission that we should expect. And then the frequency dependence of that is basically empirical. So we have two parameters, A and B, that are basically meant to capture the rising edge here and the decay part of these simulations that I showed you. And then, so this would be the DEDF, and A and B here are free parameters. My student Kyle Crocker, who looked at this, he made fits to a large number of simulations out there, and he found the range of these parameters A and B, basically saying that A is, I think, between 5 and 150 hertz, and B was between 10 and I think about 400 hertz. Yeah. So these are totally empirical, just coming from the simulations that were available to us back 4 or 5 years ago. So that's one way to approach this is we don't have the waveforms. We don't know exactly what will happen in a core collapse, but it looks like this kind of functional form explains it well. So we can try to model this with some free parameters A and B. And then, of course, out here, the front piece is just some sort of an amplitude, amplitude factor that we could also treat as a free parameter. So that's DEDF. Remember, in our master equation, we need two things, right? We need the DEDF, but we also need the RV. So the RV, the rate of stellar core collapse events as a function of redshift. So this is per co-moving volume and so on. We expect this to be proportional to the star formation rate. No delay in this case because we're the process of the stellar life for these objects is relatively small compared to the cosmological timescale. So we don't need to worry about time delays in this particular case. But we do need to put in some sort of a scaling factor, and we could put in a lambda CC here to basically tell us what fraction of the stars that are being formed end up going through the stellar core collapse process. So when we pull all of that together, we can write omega GW for this model. So we will have the usual prefactor. So let me put that out. This is a pi here, 8 pi GF divided by 3. So let's see here, 0 cubed C squared. That's what we have. There will be a factor that we called xi, which basically captures the 3 unknown scaling factors. Right? So we can put all of these 3 together and call the product of them xi. And then we have the integral over redshift, which will have the star formation rate, r star of z. It will have the 1 plus z factor and the cosmology. Remember, omega matter times 1 plus z cubed plus omega lambda. So that's the standard part from the master formula. And then we have the DEDF, where what's left here is basically just the empirical part, the 1 plus f over a to the power 2 e to the minus 2f over b. And I should be careful. This should be 1 plus z here and 1 plus z here as well. So you, because these are now redshifted, or I should say blue shifted, I guess, frequencies in the source frame. So that's the full expression for the energy density or for omega as produced by this model of the stellar core collapse. Now, if I switch back to my slides, maybe I can show some results here. So what you can do with this is, so I hope you guys can see this. Let's see, maybe I can. Okay, so maybe just give me a second. My computer is getting rather slow. Okay, so you should be able to see this more clearly. Can you see my screen? There should be 4 plots on it.
Yes.
Okay. So this comes from this paper by Kyle Crocker et al. And what we tried to do was basically we had 3 parameters. This is xi, which captures the uncertainty in the amplitude. We had the A and the B parameters. And we varied those three parameters, and we calculated omega for each combination of them, and then compare them with the sensitivity of various detectors, advanced LIGO, Einstein telescope, and so on. So you can basically see what part of the parameter space is accessible to these detectors by using these kinds of studies. And you can see that with Einstein telescope, we'll be able to do significantly better than with advanced LIGO. We're particularly sensitive to low values of A and high values of B, which means rising more quickly and decaying more slowly, which of course is not a surprise. You can also marginalize over both A and B parameters, and that gives you an upper limit on this Xi parameter, on the amplitude itself. And then you can use that to constrain, for example, this neutrino energy versus Q, the anisotropy parameter, and so on. And that maybe tells you a little bit more. It gives you maybe some information about the actual process of the core collapse, of the physics of the core collapse, and so on. So you might be able to learn a little bit about the core collapse itself. Again, you should take all of this with a lot of salt because, as I said, there is a lot of uncertainty in the models, and a lot of this is really driven by this empirical relationship that we just came up with to empirically fit the simulations. The simulations are being improved as we speak, so it is likely that we'll have a different situation in a few years. And we're actually looking at this now as well. I'm trying to revisit. Okay, so that's the core collapse. Okay, should be sharing this screen. The next thing that we can look at, let's see, we have about 10 minutes, which should be just enough, I think, is the magnetars. So magnetars are neutron stars in a, whoops, sorry about that, neutron stars in a strong magnetic field. So what I mean by that, so this is yet another model of the stochastic gravitational wave background, but due to a different set of contributors. So these are neutron stars with a magnetic field that's of order 10 to the 15 Gauss, and could be substantially higher than that as well. The story here is that we may have a neutron star that's in the presence of the magnetic field gets maybe elongated, and it may be spinning around an axis that's different from the axis of symmetry. So in this case, you have this ellipsoidal shape that has a shape of the, in the US, we would call this the American football, right? It's kind of an egg shape or something, but it's spinning around the an axis that's different from the axis of symmetry, and because of that, it's producing gravitational waves. Again, for this kind of a model, so we take, again, we need to calculate or figure out what DEF is, and we need to figure out what the rate is. The rate is, again, relatively easy because we can deal with the star formation rate, right? The rate of these magnetars will be proportional to the star formation rate. So we put in some proportionality constant lambda m, which, at this point we can, from astrophysical observation or astronomical observations, we can even make a guess of what lambda m should be, or we could treat it as a free parameter. DEF we can calculate actually in this model. Whoops, this is supposed to be D. So DEF is looks like this. Let me just write it down, and we can stare at it. There are two terms. Let's see. I'm just going to give the formula here without really deriving it. okay, plus the second term is simple f squared. A few things to note here. The first term is basically coming from the slowdown due to the so it's the acceleration of the of this magnetar due to the electromagnetic radiation, whereas the second one here is due to the emission of the gravitational radiation itself. So this is basically telling us how the two contributors, the electromagnetic emission and the gravitational wave emission, are causing the acceleration of the of this object, which in turn results in the emitted gravitational wave energy. The I here is the moment of inertia of the star. R is its radius, so it's of order 10 kilometers. And then we have this piece here, the circle piece, which is the magnetic field, B squared, divided by the ellipticity epsilon. The ellipticity here is basically the, I don't know if I have it in the notes, but yeah. So it's basically capturing the difference in the moments of inertia, I1, I2, and I3. The I3 is the main axis of rotation, I guess. So this would be the epsilon here. You can think of it as a way of parameterizing how non-spherical the object is, and it really is defined in terms of, I believe it's something like I1 minus I2 divided by I3 or something like that. But it's defined in terms of the moments of inertia around each of the three axes, and it encapsulates the non-sphericity of the objects. So this would be the D, the F that we would be dealing with, and you see that there are basically three unknown quantities here: the magnetic field itself, the ellipticity epsilon, and this factor lambda m, the fraction of the stars that end up in magnetars. So you can then do the same kind of study that I described before. You can scan the values of B, epsilon, and lambda, and try to see, calculate the omega GW for each of those values and compare them with the sensitivities of detectors. So here's an example of that. We did this study a long time ago at this point. And what you see here is we have so maybe the most interesting ones are the advanced LIGO. Probably this one here is the most relevant curve, and the Einstein telescope sensitivity over here. So what we're saying is that with these detectors, we can basically rule out this fraction of the parameter space. So very high values of lambda and very high values of epsilon over B will be ruled out from these models. Now, the maybe more interesting thing is that depending on what kind of magnetar model you have, there could be a relationship between epsilon and the magnetic field. So in particular, if you whoops, sorry about that. Okay, there we go. So in particular, if we have what is called a poloidal magnetar, so the magnetic field is poloidal rather than toroidal, or there is also a twisted torus model and so on. This gives you a relationship between the parameter epsilon and the magnetic field, and basically it looks like this. Okay, this is just an example of a particular model which relates the ellipticity to the magnetic field. And if you then use that relationship, you can take these kinds of contours and convert them into contours on this parameter beta that relates the epsilon and the magnetic field, and lambda, the fraction of the stars that end up in magnetars. And that's interesting because the prediction for the beta value depends on what kind of equation of state you have inside of your neutron star, inside of the magnetar. So you could have type 1 superconductors, type 2 superconductors, or non-superconducting interior. And in depending on the equation of state, you will have different values of beta. So with this kind of approaches, you can actually start to probe or start to learn a little bit about the equation of state of neutron stars. And these two plots basically correspond to advanced LIGO and the Einstein telescope situations or detectors. So that's yet another direction that one can take with these kinds of studies. If you assume a specific model for the magnetic field, you can in magnetars you can then start to constrain the actual equation of state in these systems. Okay, so we have 2 minutes. Let's see. Maybe very briefly, I can mention yet another situation, which is primordial black hole binaries. So the situation here is that so these are again compact binaries. So DF would be exactly the same as what we had before for the regular black hole binaries, but the rate RV will be different. So in this case, the primordial black holes would be black holes that were created in the early universe. So for example, you would maybe have a density fluctuation locally somewhere in the early universe that would be large enough to create a small black hole, which then grows over time as additional material falls in them. So these primordial black holes would be also interesting in cosmology because they would be created in the with the early universe fluctuations, which would be basically dark matter fluctuations. So if we could probe primordial black holes in this way, we could be learning something about the dark matter as well. Now, once you have the primordial black holes, there are actually multiple mechanisms for producing the binaries and for producing gravitational waves. I won't go through all of those possibilities. There is a lot of literature on this, and it's growing. It's one of the hot areas in the last couple of years. People are really studying this more. One example that we looked at, and this is a number of, this is basically when the first binary black hole detection was made. There was a paper by Kamienkovsky and collaborators asking, is this first detection primordial black hole binary? And in that paper, they worked out basically what would be the cross-section for two primordial black holes to interact with each other via gravitational wave emission and get captured into a binary. And they calculated the cross-section for this process, and they multiplied it by the density of binaries in our halo to calculate the rate of binary black holes in our halo. Okay, so I think we're out of time. So maybe what I'll do is maybe stop here, and we can very briefly discuss it or finish the discussion tomorrow. Basically the idea is that because we're dealing with primordial black holes and not stellar black holes, the rate ends up not following the star formation rate. So the evolution of the rate as a function of redshift becomes different in this case, and that might be or we might be able to go after that to measure this and distinguish between primordial and stellar contributions. All right, sorry about going over time. I'll stop here and take questions if there are any.
Thank you, Vuc. There are a few questions already on the chat.
Okay.
One is about why don't you take into account the time delay distribution bit in the case of the core collapse supernova?
You can, but typically that's a much shorter time scale than the time scale of the in-spiral of a binary, right? So it's measured in millions of years, so it's a relatively short thing, right? So the rate of core collapse events is basically the same as the star formation rate times a number.
Okay, thank you, Vuc.
The time delay is relatively short compared to the cosmological scales.
Yeah. Aditya is asking, can you explain this Q averaging in the expression, the average Q in the expression of the stellar core collapse omega GW? How is this?
Yeah, I can comment on it. So when you read these papers on the simulations of the core collapse and so on, there are several things that they pay attention to. One of them is the energy carried away by the neutrinos, which is effectively capturing the cooling of the star during the process. And the other one is how asymmetric this flow is, because that also has implications on how asymmetric the collapse will be. At least this is my naive understanding. Again, I'm not an expert on these simulations, but so those are the two things that come from the simulations, and an argument was made. I believe it was Alessandro Buonanno's paper was the first to make that argument that this asymmetry would then basically result in the gravitational wave production times some scaling factors and so on. So that's where this comes from. Is it the best thing to use? Are there better ways to approach this problem? I don't know. There may be, but that's what you can find in the literature these days.
So it's essentially a constant factor. I mean, it's a dimensionless thing.
Q here is a dimensionless thing, I believe. Yes, it's an average. I guess asterisk the averaged over all directions or something like that.
Okay. Thank you.
Yeah.
Okay, if you have any further questions, feel free to unmute and ask yourself, or you can type them as well.
I have a couple of questions. One is that typically, what is the dominant source that we expect? Is it the supernovae or the binaries?
So that is a very good question. So I think at this point we all believe that the most likely dominant contribution to the stochastic background will come from the compact binaries. And part of that belief comes from the fact that we have seen compact binaries individually, and we can make some educated guesses or estimates for how many such objects there are in the universe. And that can give us a pretty good estimate of what the stochastic background should be. If we're dealing with the core collapse or with the magnetars, there are significant uncertainties there. So if you really push the model, so if you assume that the magnetic field, for example, in the magnetars is very high, then you can get a stochastic background that is stronger than what you would get from the compact binaries. so then that becomes a question of what do you really believe you know about the magnetars, right? If you assume things of order, a magnetic field of order 10 to the 15 or so, or then probably and these beta values will probably be relatively small. You will probably not be able to detect it with advanced LIGO, for example. So this model will probably be weaker than what we would expect from the compact binaries and so on. So I guess the short answer to your question would be we don't really know because there's just so much uncertainty. But on some average, we would expect the compact binaries to dominate based on what we know so far.
Yes, thanks.
Yeah.
Hi, so I have a follow-up question to Srishti. So basically, so at one time we are having a contribution to SGWV from multiple type of sources. And my question is, how would you disentangle these multiple contributions?
It's very hard. Yeah. So we will talk a little bit starting tomorrow. We'll spend more time on how we do the search and for the stochastic background. We can measure the frequency content of the background. We can measure the directionality of it. We can measure the polarization of it. We can also measure, we have ways of trying to get at fluctuations over time. So those are the knobs that we have, that we can use to, try to discern different contributions. Beyond that, we can use other things that we know from other sources. So, for example, if we have over time a better understanding of what is the magnetic field in magnetars, and we constrain that, or if we understand the geometry of the magnetic field better for the magnetars, then maybe we can take that into our models and constrain them better, and that would give us a better sense of what the contributions are. So you asked a very, very hard question, and we spent quite a bit of time thinking about this. How do you take our measurement, which, for example, gives you a measurement of the energy density in many frequency bins? If there are different contributions, maybe one model will dominate over one part of the frequency range, another one will take over in a different part of the frequency range, and if we can catch this, then we could model both of those, or we could measure both of those contributions. In the case of magnetars, perhaps there will be a strong contribution coming from our galaxy. In which case, if you do a directional search, you will see the galactic plane is lit up as compared to the rest of the sky. So in that case, you can have another piece of information that tells you, okay, this is a galactic source rather than extragalactic. So it's certainly not going to be the compact binaries, but perhaps it will be magnetars. And maybe combination of that with the frequency dependence would allow you to pinpoint a bit more precisely what is the magnetar contribution.
So for that matter, like observing this SGW stochastic background from galactic sources, we need to build anisotropic models, right? These models are not going to work.
Right, those would be anisotropic models, and there are some out there already. This is for a number of years we've been doing the searches for the anisotropic background without really having any specific models out there. But over the last, I would say, 4 years or so, there was a series of papers that came out that actually make predictions on what the anisotropy should be. For most of them focus on the compact binaries. There are papers on cosmic strings as well, on phase transitions and so on. So we're slowly getting to the point where these models are becoming a little bit more predictive. And you know, another part of the challenge there is that measuring anisotropy will be even harder than measuring the isotropic, the monopole term of the stochastic background. It's probably going to be at least a factor of 100 a factor of 100 times weaker than the monopole. So measuring that will require very good detectors as well.
I see. Thank you.
I don't see any other questions. So thank you very much, Vuc, for this very, very interesting lecture. And we look forward to the next ones starting tomorrow.
Yeah, no problem. My pleasure. See you all tomorrow.
See you all. Bye.